So it's time for Anna's second or third talk. And it's time for Anna's. Thank you.
Thank you very much. Okay, so I want to make one correction to what I said yesterday. So yes, I found that the first example of deterministic exponential universal mixer was the work of the Dini. But I was wrong, and thank you to Andre pointing that out. So there is a previous work, so this is 2023, but there is a previous work by so it's published in this study, but it wasn't in the archive and sort of missed it. In fact, it's still in the paper, so so they have a so they also prove exponential mixing, but this paper also has enhanced dissipation. It was mentioned, and the condition of the two profiles are a little bit different. So they have a series actually of papers in 21 and 22, which they study monotonic and non-monotonic shear flows that generates for all of more. So I wanted to mention, and I also should have mentioned that Andre, I believe with this undergrad student, I was quite impressed by that. They have a numerical work in which before these, in which they looked at the behavior of this piecewise linear shear flow. And there's some interesting observation, for example, what happens if you randomize shift, randomize the time, what happens if you change the time on which you let these flows act. So it's a very nice paper, and so I recommend to look at it. Okay, so yesterday I presented one example of a very different example, which we do everything by hand. It's the geometric construction of a W1P for P less than infinity. And I want to give you a very brief idea of the other example, which we call the piano snake, because it is sort of follow the construction of the piano curve, and it's a strip. Okay, so if you bend the strip, it looks like a snake. Okay, so so it's the same exact idea. So it's again, you give the evolution of a set. And you use the smooth evolution lemma, which I mentioned yesterday, to construct the velocity field. But the construction is a lot more involved. So I'll just show you one slide with some picture in it. Okay, because if I were to really go into the details, it's quite involved. But the idea is the same. The construction is not so similar, it's quite so similar. That is, so the image at time 1 of the initial set is not an exact replica at a smaller scale, but it is a suitable combination of rescaled copies from a finite family of initial patterns. So that gives you more flexibility to adjust things, and that's why you can bypass this problem that you're not allowed to have topological changes because of low glitches. And the initial condition is a strip centered around the median segment in not in C2, D2, that's a misprint, I corrected. And as I said, in some sense, not exact, but in some sense, the time evolution follows the iterative construction of the piano curve. I should mention that you can make this actually into, and I will use that in what I plan to talk about today, which is loss of regularity. You can make the construction so that U is smooth, because the only place where you have some jumps is actually where you reach the boundary of the torus, okay, because of periodicity. So there potentially you have a jump, but you can, because all our construction, remember, are local, you can actually smooth out that region without losing actually on the rate. Okay, you can lose a little bit on the constant, but not on the rate. However, you still control only the Lipschitz. Okay, still a Lipschitz example. But the fact that you can be made smooth, I will use for the loss of regularity. Now, so here's just a picture. So the evolution of the set was like this. Okay, so so here, and I should say that you can also generalize this example to functions that are approximately binary. So my initial condition will still be like a strip, but instead of having a steep jump here, you can have just a decay. Okay, so you can smooth things out. I will also use that for the loss of regularity, so you can think that you can make the initial condition be C infinity. And then we evolve it, okay, we evolve it into pictures that are composed by straight pieces and curved pieces. So actually my family of configuration, it's all drawn from two configurations, an exact replica of the initial strip and then a curved piece here. And then what you can prove is that you can repeat this construction, okay? Still drawing just from these two families, okay? And in the end, and the way that you do this, in some sense, so it's given here. So if you look like at the median line here, the construction looks very similar to what you would do for the construction of the piano curve. So the only places where you have trouble, so the evolution is C infinity inside, but the only place where you have trouble is when you meet the boundary of the torus. Okay, so there you have potentially jump in the derivative. So the derivative is bounded, but you are no better than Lipschitz, but you can smooth things out a little bit. Of course, you have to be careful because, you know, at the first step, your trouble is only here and here. But of course, then when you move it to later times, that trouble could propagate, you know, in that set. So you have to show that, you know, the smoothing that you do here can be controlled down the line, but that can be done. And so what I want you to take away from this picture is that you can construct an exponential mixer where the initial condition is C infinity compact support, okay, and the velocity field is also C infinity. Also, well, I mean, I'm on the torus, so the support is obviously compact, but you control only the Lipschitz non-uniformity. Okay, so I will use this to show loss of regularity for solution to transport equation, which is my next topic. Okay, so as I said, these optimal mixers are useful to investigate the ill-positiveness of the linear transport equation, but of course with the rough, but not rough, that is the Sobolev class velocity. So here I want to point out that we're still thinking about in the loss of regularity case, still the Permalions, so renormalized solution. So there's uniqueness, there is existence, but you have a ill-posedness in the sense of Adamant. There is discontinuity of the solution map. And if you go to rougher data, you can also have ill-posedness in the sense of loss of uniqueness. So in the first example, I already mentioned that the first example, the one with the pinch singularity, shows that you have discontinuity of the flow map pointwise, because remember, you can compress a segment to a point in finite time, and you can compress a point to a segment, and you have no uniqueness of trajectories starting from points along these segments. But here I want to investigate discontinuity in Sobolev spaces. And once I have that, the result will be this loss of regularity for solution of transport equations. And so let me make a few remarks, okay, before I do that, that actually, as I said, if you go to rougher data, so data that are BV and not Sobolev, you get non-uniqueness of weak solutions. I already mentioned this yesterday, but I want to say one more word. So recall this slice and dice example, the checkerboard patterns. There was also a report today of finite time perfect mixing. And by linearity, if data equals 0 is always a solution, and you have time reversibility, but for weak solution, you have that if you have a finite time perfect mixing, then you have non-uniqueness for solution. In fact, this was the original motivation in the work of the Paul that's also called today by Chris. I want to just say that this example is optimal in the following sense. So if you think about it, okay, the way they use mixing, if it's a piecewise constant shear, is because it's creating interfaces, okay? So the more interfaces you create, the better you mix. And also, if you think about it, the total variation norm view, okay, is proportional to the length of the interface that you create, okay? So at each step in the construction, you double the interface you create. So you can estimate how fast the total variation norm of your vector field U grow in time. So it doubles at this successive iteration on time interval of length to the minus n. And remember that the finite time mixing time is exactly the sum of this geometric series. So if you put all of this together, you can easily see the total variation norm of U of t is actually proportional to 1 over the time to mix. So in other words, U is in weak L1 in time with values in the space of bounded variations. And the Ambrosius result says that you couldn't have this if you were L1 in time with values in BV. So you see, from that point of view, the regularity of this flow is optimal. Okay, you cannot do better than that. Well, okay, you can always squeeze maybe some strange spaces in between, some kind of Orlick spaces in between weak L1 and L1, but okay, normally speaking, this is optimal. Okay. And the reason why you have an optimal example, which is so simple, is because, okay, you work in BV, right? So BV is your friend here. So let me discuss the other impulseness that I want to explain, and I'll give you two examples, one this morning and one this afternoon. They're two different constructions of loss of regularity. Yes?
Sorry to interrupt you. But if you rescale time, wouldn't that work with that L1?
Yes, so you can make this L infinity in time, and then it's an exponential mixer. You're absolutely correct. So the point is that here,
You want to talk about regularity.
Exactly. So you're absolutely correct that I can, by changing the time in which I let this vector fields, I can get all sorts of different decay. In particular, that was already observed by Alberto in Brazil, that if you let these shear flow act on time 1, then you get an exponential decay.
Yeah, okay.
Yeah. But here, the point is, I want to go as close to the optimal regularity as I can. Okay, so that's what I mean. But you're absolutely right. If I slow it down, I can, I can make this actually be L infinite in time. But of course, then I don't have non-unique. Then I have unique.
And then in principle, you can do this with every, also with your construction, right? I think also with the super vector, if you just rescale time properly.
Yeah, I guess you're right. In the sense that you can always, if I make that X on smaller time intervals, but then it's harder to see how the PV norms, the total variation norm.
No,
Yeah.
Rescale time. Then you can also.
So if you make it X, so I agree that you can rescale any of these examples so that the norm blows up at the finite time to get finite time mixing, and the norm will blow up. The point here is that in this example, you just get exactly, as close as possible. So in the sublet example, I don't think it would be weaker one. I think it would blow up faster.
Yeah.
Yeah. So that's, but you're right, I can always speed this construction up to a finite time mixing, but then the norms blows up faster. So this example just show you that, you know, you are very, very, very close to being.
Yeah. I never got this.
Okay, okay, what I want to present is this loss of regularity, okay, and why, first of all, this is for the student, why there is a connection between mixing and loss of regularity for solution. Well, so I'm looking only at mixing due to stirring alone, okay, and so you are creating small scale in the Drexel field that is large derivative. This was already mentioned several times. And so in some sense, there should be a connection between mixing, especially mixing with optimal rates, and the growth of sublevel norms. And this is encoded in this simple interpolation inequality that the L2 norm squares of theta is bounded above by the product of the positive HS norm and the negative HS norm. Of course, you have to assume something happens. You have to assume, of course, that theta is in checks, okay? So if theta is regular enough, you have this interpolation inequality. So note that our vector field, so we're talking about sublevel regularity here. So theta is a renormalized solution, so the L2 norm is conserved. So this is a constant. So that means that if the H minus S norm goes to 0, then the HS norm has to grow. Now, of course, the HS norm could go to infinity without the negative sublevel norm go to 0. But if you already know that the negative sublevel norm goes to 0, then the positive norm has to explode. And so, you know, that's the way that you can quantify the fact that if you are mixing, you have growth of sublevels. So I will exploit this fact to basically show that you can speed up the growth of the norm to an instantaneous flow up. That's what happened. Okay. And for that, we use this modification of this Lipschitz example, which I showed you, that we can make it into a C infinity example. So here's the theorem that we can prove. So it's an example in the whole space law in the torus. There is an easy way, and I will make a comment about that for our example, since they are local, to be transferred from the torus to the whole space. So, and also to go from 2 dimensions to higher dimensions. This is an example in any dimensions. So there exists a C infinity complex support function in RD and a vector field U, which is bounded uniformly in time and space, that has additionally the following property. First of all, U is uniformly in time with values in W1P for any P, except infinity, of course. It cannot be Lipschitz, but you can go as close as you want to Lipschitz. And if you call theta the unique weak, and it's also a Lagrangian solution of the transport equation with this velocity U and this initial condition, then theta is a bounded solution. So this is to say that this is not from the point of view of the weak solution of transport equation. This is a good solution. Okay, it's a good solution, is unique, it's Lagrangian, it's bounded uniformly, but nevertheless, from the point of view of regularity, it's as bad as it gets, because you go from C infinity instantaneously to just be L infinity. So it loses all sublevel regularity, including fractional regularity, instantaneously in time. And in fact, I will make a comment that there is some tiny regularity that gets propagated, but in the scale of sublevel spaces, you lose everything. In addition, in some sense, the irregular set of theta is as small as it can be, because you can prove that U and theta are compactly supported on a cube and are smooth outside of a fixed point in space. So the singularity set is just a point, okay? So this theorem, as I said, provides example of total instantaneous loss of sublevel regularity, including fractional for weak solution to linear transport equation. And to my knowledge, it was the first example of its kind. Of course, there is a connection with the norm inflation. I will make a comment about that later. And since theta is the unique renormalize and hence Lagrangian solution of the transfer equation, this theorem implies that you have a pretty severe discontinuity of the flow map in sublet spaces. So this is this Hadamard deposit in some sense, but from the point of view of the flow map in sublet spaces. So, in fact, independently, Jaban in 2015, my colleague showed directly discontinuity of the flow map, but he uses a random construction. And there's also work in 2020, but Beniti Bianchini also on discontinuity of the flow map. Let me say that by contrast, if you use Lipschitz, and here you can get as close as you want to Lipschitz, then the flow map is also Lipschitz. So of course the Lipschitz constant can go exponentially in time, and the regularity of theta, at least up to Lipschitz, is propagated. So you really have that when you go from Lipschitz to sublet, you have this, dichotomy in some sense. So something really dramatic happened to the flow. Some regularity of theta does get propagated if you have W1P regularity, and it's essentially only the logarithm of the derivative. So think about taking Fourier transform, okay, and you have, that's not exactly how it's defined, but, morally speaking, you just multiply the Fourier transform you function by the log of the free, okay? And that gets not conserved, but propagated. And this was first observed by Léger. And then Brouet and Goyen proved using some modification of our example that this result is sharp. In some sense, you can really do no better than that. Okay. And then later on, it was shown by Ghisi and Bubino, and last year by Bianchini and Zinza, that in fact this loss of regularity is a generic phenomenon. But what I mean by this is that it's generic in the sense of bare category theorem. So the set of initial conditions and flows where you don't have this is a meager set. Okay. I should say, of course, that our example is not universal, right? So, I mean, you give me, I give you one initial condition and one flow for which that happens. As I said, there are some connections with norm inflation phenomena for PDE. Of course, we also use growth of norm, but here really this is in some sense a linear phenomenon in the following sense that on one hand, my vector field U, if you really look at the construction, is a non-linear function of the solution. So in some sense, I'm not really solving a linear equation, right? It's a non-linear construction. But I'm using the linearity of the equation in the sense of superposition. Okay, so I'm using superposition to speed up the construction. If you think about norm inflation for nonlinear PDE, this is a well-known phenomenon of Navier-Stokes. Well, number one, it's typically happening in much rougher spaces, not in LP initial conditions or, W1P. And secondly, there you're really using the non-linearity for the norm inflation, okay, the fact that you have interaction. And so on one hand, you have the non-linearity that helps you to grow the norm, but on the other one, you have the difficulty that you don't have superposition, and hence why typically you don't get this instantaneous blow up. So you have norm inflation, so it takes time to lose the regularity. There is recently work on the Euler equation that is a loss of regularity. I will comment about that later. Okay. So the main idea of the proof is really, really easy. Okay. And I like this result very much because it's a very simple idea, but it turned out to be a powerful idea. So we use the mixing to grow the sublet norm exponentially, and then I rescale everything to turn the growth into an instantaneous blow up. But you have to be careful, and it turns out that this rescaling is not very flexible. So we first thought we could prove a stronger result, and it turns out that by this method we cannot. And we have to use a different construction to extend this result a little bit. So let me explain, okay? So first of all, we need, this is more again for the student, so we need a technical lemma to teach the fractional regularity, because the HS norm for SP between 0 and 1 And that's the main reason, by the way, why we use L2-based tablet norm for the tracer theta. So the HS norm are not local, but nevertheless, you have almost a decoupling for superposition of function with well-separated supports. And I'll state the lemma in a minute, but let me say that the way to prove this, this sort of almost linearity of the norm, or locality of the norm, if you want, is to use Galliardo semi-norm. Okay, so you can write the semi-norm in HS as an integral equation, and that's what we use for this lemma. And that's the main reason why we use L2 based. We believe that L norm should have the same behavior, but okay, we didn't do it. So here's the lemma. So again, I'm in the fractional range in 0 and 1. And I have functions, finitely many functions that are supported on compact set Ki that I was separated. That is, there are in open set omega I, which are disjoint. And so the distance of Ki to the complement of this open set, I'm going to call lambda I. So the distance between Ki and Kj is at least of order lambda I. And then what you can prove is that if you give me any function in HS which are supported in this Ki, then I can bound from below the sum, the HS norm of the sum of this function, but the sum of the HS norm. But of course, I pay a price, and the price is in terms of the L2 norm with 3 factors, which depends on S and depends on lambda I. Of course, it degenerates as lambda I goes to 0. Okay? And we will need to extend this formula to series, and you can, as long as the right-hand side is positive, which is our case. Okay? So we can make this into series, which is what we will need to do. So, okay, and as I said, we state our result in the whole space. So we need to lift the construction of this exponential mixer from the torus to RD, to R2 first and then to RD. And to go from the torus to R2, there is really nothing because our constructions are completely local. So you just extend it by any flow you want. And you choose one where you can extend the construction. So how do you go from d equal 2 to d greater than 2? Well, it's in a straightforward fashion. You simply observe that if you give me a compactly supported bound function in Rd minus 2, and I define, u bar and theta bar like this. So I take my u and theta in 2 variables, and then I multiply by eta in the remaining variables. Then u bar is still divergence free. Okay, it has the same regularity, and theta bar solves the transport equation with velocity bar. So in some sense, you're saying that you're doing nothing in the other direction. Okay, but that's good enough because you have enough growth in the 2 directions. Of course, this says immediately that you can, that this is gonna only work for very special initial condition, because obviously if you take a generic initial condition, you could do nothing in these 2 directions, and then this method will give you anything. But okay, it works for this example. So here's the sketch of the proof. So we're going to construct u and theta as sums, a superposition of un and theta n, where un and theta n are obtained by scaling u0 and theta 0. So here, u0 and theta 0 are not initial conditions, but rather initial step in an iterative construction. So once you construct u0 and theta 0, you simply need to be careful about rescaling, and you have your solution. And the reason why superposition works here is the equation are linear, and the support of this un and theta n are disjoint. So let me start with the construction of the basic elements here. So we're going to take the Lipschitz exponential mixer and modify it to make the velocity and the scalar to be smooth. And then we're going to lift it to RD using this construction here. And note that if U and theta are compactly supported in R2, U bar theta bar are compactly supported in RB. And so you can always arrange it so that they're supported on the unit cube. So Q0 will be our initial cube, and I will have this U0 and theta 0. And you want to do it so that you have control on the norms. So you do this modification in such a way that the following norm bounds hold. So first of all, you still want the U0 theta 0 are L infinity. That's not difficult. And you still want that the average of theta 0 is 0 over the cube. But here is the control of the norm. So U is infinity, right? So it belongs to any WRP, SP, okay, for any P and any S. And the control is this. If R is 1, okay, so you are in W1P, and P is not infinity, you have uniform in time control. On the other hand, for any other norm, you have an exponential control. Okay, so the higher norms can grow exponentially fast. And for the solution of the transport equation, you have that the negative Sobolev norm go down exponentially, and this is true for any negative norm. So particular by interpolation, since the alto norm is preserved, we have that the positive norm will grow, except for the constant, the prefactor will grow at the same rate. Okay. So this will be the initial step in our construction, and then we rescale to get the loss of regularity. So here's the construction of theta n and un. So there will be 3 sequences here, lambda n. So one that gives us a rescaling in time, one that gives us a rescaling in space, and one that gives us a rescaling in amplitude. Lambda n will be the rescaling in space. So I take a sequence of positive numbers that go to 0, as n goes to infinity, to be chosen later. And then my solution and my velocity will live on the union of cubes, of countably many cubes Qn, that are dilations, but contraction, in fact, of the unit cube of a factor 3 lambda n up to rigid motion. Okay, so you should think that you can rotate and translate. I will not say this explicitly. And I'm going to choose the center of this cube so that they are pairwise disjoint. So you should think that this looks something like this. And because lambda n goes to 0, this will converge in the sensor set to a point. And this is the only place where the construction is not infinity. We also want that U and theta have compact support. So I want that the measure of the union of this cube is finite. So that means that I have one constraint besides lambda n going to 0, that the sum of the lambda n has to be less than infinity. So this is my first constraint A. And I will have several other constraints. So up to translation and rotation, then I define UN and theta n simply by dilation. Okay, so I dilate in space by a factor lambda n. I dilate in time by a factor of tau n, which needs to be chosen. Okay, and I will, so this factor in front of the n is to make sure that I still satisfy the transport equation. And I will also need to put an amplitude factor in front of the theta n. So gamma n will be how much I increase the amplitude of theta n, and also to be chosen later. And we need to make sure that this gamma n is not too large, because we still want the initial condition to be C infinity. Okay? So the meaning of this parameter is that lambda n is a space scaling, tau n is a time scaling, and gamma n is an amplitude scaling. And so you can see, by the way, that you can, in fact, so I often get this question when I present this result: can you make the singular set worse? And the answer is yes. Okay, in some sense, we wanted the smallest singular set, but I can make it if I can make the singular set to be a countable union of points. Okay, I cannot make the singular set to be a line, for example, or to be any set that has accumulation points, because in this construction I have to make sure that theta n and un lives on these joint cubes. So it's an interesting question whether you can modify this construction to say, specify that you will blow up on a line, or if you can even make this point go to infinity, for example. That I don't know. To be possible, but so then the construction of u and theta it's done, because we simply define u to be the sum of the un and theta to be the sum of the theta n. And u and theta are well defined, at least almost everywhere. In fact, are well defined in any local norm, because the qn are pairwise disjoint support. And the fact that u and theta also theta is also defined in the fractional norm, I have to use the lemma that I presented before. Then you can check that sorry, not theta 0, or sorry, because theta 0 and u0, so theta 0 is the weak solution of the transfer equation with velocity u0. Then, of course, theta n is the weak solution of the transfer equation with velocity un. And then from there, you can check that theta is a weak solution of the transfer equation with velocity u. And the initial condition is the sum of the initial condition of the theta n. So the question is whether you can take these three parameters that you have, the lambda n, the tau n, and the gamma n, in a way to control the norms. So, and I will use rescaling, of course. In this case, notice that we do rescale the measure. So the rescaling is not that of the torques, okay, it's that of RD. So by the behavior of the Lebesgue-Sobolev norm and the rescaling, you have the U is uniformly in W1P if this series here is finite. What exactly it is, it's not that important, but notice that I have to control exponential term and then this ratio here. And then I also want you to be bounded. That simply means that the ratio of lambda n of theta n, which is the amplitude of the un, is uniformly bounded. Okay. So B and B tilde has to do with controlling the norm of u, the velocity. But I also want to control the norm of theta. And so first of all, I want that the initial condition is in H sigma for every sigma. And that means another constraint of gamma n and lambda n written here. And I also want that theta is uniformly in L infinity, which simply means that the gamma n are bounded. So immediately here you see that I cannot make the amplitude go to infinity. I only have a little bit of leeway to adjust things with gamma n so that some of these things are under control. Okay. Lastly, I want to prove that theta of t is not in HS for any s positive for any t positive, and that means that this series has actually to be divergent. So you see, I have many constraints, and at the very beginning, we weren't sure that we could fit all of these constraints, but in fact, you can. And here's the explicit choice of lambda n, tau n, and gamma n. So we're going to choose tau n to be 1 over n cubed, and lambda n to be exponentially decreasing. And then you can show that this was the constraint on the support of the cubes, and these two were the constraint on the norm, the L infinite norm and the W1P norm of the velocity field. And you can see that they work, but unfortunately only for r equal 1. So the rigidity of this construction is unfortunately that the rescaling is so rigid that you can only make it work with r equal to 1, not with r greater than 1. And then the amplitude here actually is there to enforce this condition here. So in fact, you have to make the amplitude go to 0, not to be of order 1. And if you make it go to 0 exponentially fast, then you have these two conditions on the regularity of theta. Lastly, you have chosen all of your parameters, so you have to hope that this last condition is satisfied. And in fact, it is satisfied because we have that this factor here is positive. So this will control what happens for gamma n. Okay, so, and as I said, okay, so you write it down and you get this. So how much more time do I have? A minute, okay. So so maybe I will just make comments. I will finish a little early and I will give the other construction for the afternoon since it's completely different. But there are two natural questions that arise here. Okay, first of all, initially we thought that we could make all the norms to have the explosion of the loss of regularity for vector fields U that are in all Sobolev classes that do not embed in the Lipschitz class. In other words, that we could control more than one gradient provided the integrability is low enough. But unfortunately, our construction doesn't allow that because the scaling is rigid, as I said. And so this is one natural question. The other one is, can we give a universal construction for U that makes most of the initial condition theta zero blow up? Now, I don't expect that it's possible to find a single U that does that, but the idea is, can I find a construction which is universal that give me a U that makes theta zero blow up? And so we in fact were able to give a partial answer to these two questions. And the way to do that is to get away from mixing. So in other words, we will not use a mixing flow, but we will use a flow that directly makes the norm grow. Okay. And the reason why mixing flows are not optimal here is that in order to control the higher norm, you really have to work locally. And mixing flows will make the Sobolev norm exposed everywhere. And that's too strong of the conditions. So the example that I will present in the afternoon, which is joint work with Gautam, Gianluca, and Tarek, is in fact completely different. Well, not completely, but you know, it really doesn't use any mixing flow. Use shear flows. So I will stop here and I will present the other construction that is happening. Thank you.